Hey, welcome back. It's Mr. Boyd back at it again. Today we're going to talk about position vectors and get into the part of vectors that I really like where they come alive, the actual applications where they're actually used. So let's get through the position vector stuff first so we can understand that. That's going to come up a lot, especially in video 4. That's going to come up a whole bunch. So let's get that out of the way here first. The deal with a position vector is, normally we learned in the last video that a vector is just a direction and a magnitude. However, there is a way of writing a vector so that we know where the vector is, or its position or its location. So the notation for that is like this, and the wording for it is position vectors. Okay, so over here we talked about last time, like if we had AB, that's a vector that starts at A and goes to B. Well, here, this is a vector that goes to A, but where does it go there from? From O. What do you think O is? O is specifically the origin. So when I go to sketch this vector, I have to start at the origin, and then it says, please go 3 to the right and down 7. So 1, 2, 3 to the right, down 7. So it's indicating that that's point A. And so what we now know from looking at that vector is that point A has coordinates 3, -7. And so one of the main things you need to know about position vectors is they are a way of giving us coordinates of a point. And if you get a written question that refers to a position vectors always start from the origin. That's why they give us a coordinate. Now here it's obvious, it says, okay, there's an O right there. But even if it didn't say OA, if they said 3i minus 7j is a position vector, we would know that it had to start at the origin. So with that, let's see if we can answer a question like this one. Point C has a position vector of -4, -2. What does that tell us about the point? Okay, let's make a quick sketch of it. Because it says position vector, that tells us that we're starting at the origin, we're going left 4 and down 2. So point C is down here, so left 1, 2, 3, 4, down 1, 2. So that tells us that point C has coordinates of -4, -2. And you go, why? Well, what's with the games? Why didn't you just tell us the coordinates? The deal is, it's just using the notation of vectors to describe locations. So yeah, coordinates is another way of doing it. This is just the vector way of doing it. And in video 4, we're going to see why it's actually better with vectors to write position vectors rather than coordinates. It actually becomes less work, believe it or not. We can also use angles to write vectors. Now, when we say angles, and you probably want to pause the video and write this right here down, you also need to know that we're talking about unit circle angles. And the reason for that is that when you go to type an angle in your calculator, it knows unit circle angles. In fact, that's the only kind it knows. Like all the trig stuff, sine, cosine, tangent, all that, that's going to be in reference to the unit circle. And so we make sure that our vector language works the exact same way. So what do we have here? We have a way of writing a vector is you can take the magnitude of the vector multiplied by I cosine theta plus j sine theta. Now, if you try to memorize this just blankly, I mean, you could probably memorize it. It's not that long. But take a minute and realize something. I, we learned, is a vector that only points to the right. In the previous unit, we learned that cosine is an x value. Well, x's go left and right, i's go left and right, that's why they're paired. The same thing with j's and sines. We learned in the previous video that the j vector goes up, and sine is a y value. That's why they're together, okay? So let's do this example here. If we have to sketch the vector, r equals 7 times I cosine 50 plus j sine 50, what that means is figure out where on the unit circle is 50 degrees. That's out here somewhere. And it says the length of that vector, or the magnitude, is 7. And I'm going to go like this and call that 50. Because recall, on the unit circle, 0 is out to the right. So that's all that notation says. And that may seem really cumbersome, but actually it's going to make our application calculations way easier than if we didn't have it. So we'll see that in just a second. With that understanding, it'll be common that we're asked to find the direction angle of a vector. So let's do the direction angle on this one. If you haven't noticed yet, there's a pretty good theme in this unit that we probably want to try to visualize the vectors in order to understand them. So that's what we're going to do here. This one goes 2 to the right and 2 up. And so I'm going to draw it out like this, 2 to the right and 2 up. And we're asking for the direction angle, the location on the unit circle that is describing that direction. So we're asking for that angle. Now, okay, some of you can probably look at this and you remember from geometry that's an isosceles right triangle, and I mean they make that a square. This is an isosceles right triangle, and therefore the direction angle is 45 degrees. And that is true, but I want to show you a technique that works no matter what. Okay, so what I'd want you to notice here, this is a right triangle. We're looking for the angle here. We have the opposite and adjacent sides. And so you may remember from geometry, like SOHCAHTOA, that tangent is opposite over adjacent. So we're just going to do tangent of theta equals the opposite over the adjacent. When you go to type that in, you're going to type in tan inverse of, you can either write 2 over 2, and I'll write that here in the video, or you could just type 1, since 2 over 2 is 1. And if you do that correctly, you will get 45 degrees, and you will be right, which will be awesome. Another thing I want to point out to you, this will save you a little bit of work. We learned in the previous unit that tangent is y over x, or sine over cosine. That is not different than what we learned in geometry. Well, wait a minute, it says SOHCAHTOA. Yeah, I know, but it's the exact same thing. So take a look. Isn't that what we did here? Didn't we put the y value on top? The opposite side was the y value. And the adjacent side, the one on bottom, was right here. We put that on bottom. Okay, so it's not a coincidence. They're designed that way. In fact, anytime you have something drawn like the unit circle, this relationship will hold up. And if you want to do it as y over x instead of SOHCAHTOA, you can absolutely do it that way, and it will work out for you. Okay, let's do this one. This would be a great chance for you to pause the video and test your skills. Okay, if you're ready, hit play, and I'm going to walk through it. 3 to the right, 9 down. So 3 to the right, 9 down. There's the vector. 3 to the right, 9 down. I want to know the angle in there. That's the unit circle angle. So I'm going to go with tan inverse of the opposite over adjacent, or the y over x. So that's going to be 9 over 3. Notice I'm not actually using the negative. I don't have to. I'm treating it like a geometry question right now, and that's why I'm going to get away with this. And then I'm going to take a minute, excuse me, while I type that in. And I get 71.6 degrees. Now, did you notice that that doesn't answer the question? Remember, the direction angle is asking for the unit circle location, and the unit circle location of 71.6 is out here somewhere. So we've got to be a little bit careful. Maybe I'll redraw the picture, try to do a little bit neater, and I'll try to label the important information. So our vector goes down like this. What we really just learned is that this angle is 71.6. So I'd want to remind you that on the unit circle, this is 0 degrees, that's 90 degrees, here's 180 degrees, here's 270, and if you went back around, you could also call this 360. So the direction angle is somewhere between 270 and 360. The easy way to do that is to take 360 and subtract off 71.6 degrees. And that's 288.4. So that actually is the direction angle for this vector. So be careful of that. You have to pay attention to what quadrant you're in. When you do tan inverse stuff, your calculator will tend to give you an acute angle, which means if you say that as your direction angle, all your direction angles will be in quadrant 1, but we know there are 3 other quadrants, so please be mindful of that. That's another reason why it's really important to draw a picture. And one more. What is the angle formed by the vectors I plus 2j, and that shouldn't say 2, that should say u equals 2I minus j. Let's draw the picture. Now, when they say the angle formed by the vectors, they do not mean head to tail. We learned in the last video that was for addition. When we're looking for angle between vectors, we're going to draw them tail to tail. And so you're going to see me do that here in this example. All right, let's do our vectors. So that's I plus 2j, so 1 to the right and up 2, so maybe somewhere up here. And 2I minus j, so 2 to the right and down 1, so maybe somewhere in here. And so notice, we actually have 2 angles. We have the angle on the right side, and we have the angle on the left side. And they're not the same angle, so which one do they want? When they ask for this, they're actually always asking for the smaller angle of the 2. So what I'm going to do is I'm going to dive into this picture just a little bit more. I'm going to try to label it up so the information makes sense, and I'm going to try to make triangles out of this. So since that went up 2, that's a height of 2, and that's a length of 1. This second triangle, it goes to the right 2, and it goes down 1. So to find that angle in between them, it's as easy as find this angle, find this angle. Since those are adjacent angles, we could add them together, and that would give us the total angle between the vectors. So I want to show you the quickest, easiest way to do this. To find a direction angle, because I know the 2 side lengths, and by the way, a vector will always give you the x and the y components. That's what a vector is. Sometimes the z, but always the x and the y. That's why it will always work to use tangent inverse to find this angle. So I can use tan inverse of y over x, so 2 over 1. And to find this second angle, I can do tan inverse of the y value, 1, and the x value, 2. So, or opposite over adjacent if you prefer that. And I'm going to take a minute and type these in. Let's see what we get. For the first one, I get 63.4. For the second one, I get 26.6. Make sure you round them correctly. And when I add those together, I get 90 degrees. That's the angle between the vectors. That's it. Now it's time for us to get into the exciting stuff, to see where the vectors really come to life a little bit. Before we can do that, we do have to make sure we know what a compass bearing is. Okay, make sure you take really good notes on this. This is how a lot of airplanes navigate. They also use GPS, of course, and boats as well. And yes, boats use GPS as well, but they do use actual bearings like this. And especially like in a case where they're doing like a search and rescue or they don't have GPS, this is really, really important stuff. Okay, so first of all, let's compare and contrast this to the unit circle. So we have bearings on the left. I'm going to have unit circle on the right. On the unit circle, we start at 0 and we go counterclockwise, making this 90 degrees, 180 degrees, and 270 degrees. The compass works in a similar fashion. It starts at 0 right here, but notice it goes clockwise. Please include visuals in your notes, with 90 being over here at east, 180 over here at south, 270 at west, and then it goes all the way back around to 360, and 360 is the same as 0, which is exactly what we learned on the unit circle, except it's in a different spot. Okay, so that has the potential to give you some confusion, so be really, really careful. Now, your calculator does not speak bearing. If you type bearings into your calculator, you're going to get ridiculous answers. So please be mindful of that. Make sure that everything you type into your calculator is a unit circle value. Sometimes we're going to have to convert it. So like, for example, if we said a bearing of 228, let's convert that into a unit circle number. So let's find 228. If 180 is down here and 270 is over here, 228, I can actually just look on here. So 228 is right about there. And what I'm going to do to figure this out, I'm going to figure out how far is 228 from 270. Well, let's do 270 minus 228, and I get 42. So this angle right here is a 42-degree angle. Then what I'm going to do is I'm going to say, all right, where would that be on the unit circle? Well, it's the same spot. It's just going to be a different number because we have a different numbering system. It's still a 42-degree angle, but now if this goes 0, 90, 180, this is just 42 degrees more. So I'm going to do 180 plus 42, and I get 222 degrees. So if we were going to type something in our calculator to do a calculation, we would have to use 222. If we use 228, we'd get some kind of crazy answers. It seems like a little technicality, but it's going to make a big difference in these questions. Let's start with a basic one. A boat travels east at a rate of 8 knots. Knots, by the way, is nautical miles per hour. You can think of it like miles per hour for this question. The current, meaning the water that's flowing, starts moving northwest at a rate of 2 knots. What's the new speed and direction of the boat? All right, I'm going to show you how to draw it, guys. So east at 8 knots. East, 8 knots. Then we're being affected by the current. When something's being affected by more than one thing, that turns out to be well described by vector addition. So I'm going to draw this head to tail. Northwest is like this, at a rate of 2 knots. One thing we might think about, if the boat's trying to go east, is the current helping it or hurting it? It's definitely not pushing it forward faster. It's slowing it down and pushing it kind of like back into its relative left. So it's not really helping. That may come up later. We'll want to use that information to double check our answer. We have to find the new speed and direction of the boat when that current is given. And because it's vector addition, what that's going to look like is this. So we have a visual model on the left that describes it. Now we need to get into doing the math. Here's the easiest way to do it. We recognize that what this is going to be, it's going to be what the boat's trying to do, plus what the current is trying to do to it, and that will give us the result. We can write vectors for each of these, and some of them are easier than others. Like, for example, the boat is only going east. It has no vertical component. It's not going north or south at all. So its vector is 8, 0. Now, when we look at the current, that's a little bit more difficult. I'm actually going to draw the current vector also sort of on a compass over here. It's going out to the left like that. And if it says northwest, let's assume that it's halfway in between north and west. So when we go to write the vector for the current, we'll have to use a direction angle. So let's practice writing this out the way we learned a minute ago. Like we learned, I believe it was R equals magnitude of V I cosine theta plus, J sine theta. So we're going to write this out in that form, and we're going to write the current vector. The magnitude was given, that's 2. And then we're going to have I cosine of the angle. Okay, what's the angle? It's a unit circle angle. If 90's there, and that's 45 more, because remember 90 is up on the unit circle, not on a bearing, on the unit circle, and we're using unit circle values here, that's going to be 135. So plus J sine 135. Now I'm going to switch to component form. It turns out, and that's what I already have here is component form, it turns out that when you switch to component form, it's a lot easier to type it in the calculator because you're not dealing with i's and j's. So the way I'm going to write that then is going to be with this distributed, and it's going to look like this. 2 cosine of 135 J, except I'm not going to write J because it's component form, so it's 2 sine 135. Now, some people will get confused because they say, wait, why is the cosine on the left and the sine on the right, and why are they different? Well, remember, the first part of the vector tells us what's happening in the horizontal direction, the x direction. And the second part tells us what happens in the y direction. And also recall from our unit circle learning that cosine represents an x value and sine represents a y value. That's why they go in this order. Now, to get the result of this, all we do is we add vertically like we did in elementary school. So what I'm about to type into my calculator, as I'm sitting at home here, I'm going to type in 8 plus 2 cosine 135. And when I do that, I get 6.59. On the left or on the right side, I'm not going to type it in. You could type in 0 plus if you want, but that doesn't do anything. So I'm going to type in 2 sine 135. And I get 1.41. Truly, we have already done the hardest part of this question. Okay, we haven't answered it yet, but we've done all the hard work. So now what we have to do is we have to figure out what's the new speed and what's the new direction. So remember, from this picture, the way we labeled this, the speeds were magnitudes. So what we have to do now is find the magnitude of this vector. The easiest way to think about it is if we take a minute and draw out this vector. This is a vector that goes 6.59 to the right, and it goes up 1.41. I like to pause here and make sure that matches the original picture. You see how I have this going up and right, and our original was going up and right in the picture? So now I can kind of say, all right, so my calculation is making sense so far. I don't think I've made a major error. So I want to know the magnitude. That it would be square 'em, add 'em, root 'em. So 1.41 squared plus 6.59 squared. Take a square root of that. I'm going to take a moment here and type that in my calculator. And I get 6.74. So 6.74 knots is my new speed, and that's KTS for knots. And then we also need to find the direction. Well, the direction's an angle. So I'm going to just make sure I'm understanding that's on the unit circle. 0 would be there, 90 would be there, my answer's somewhere in between. Remember that the way that we find a direction angle is with tan inverse. So tan inverse of y over x, 1.41 divided by 6.59. So I'm going to take a moment here and type that in. So tan inverse of, don't forget your parentheses when you type this in, please, 1.41 divided by 6.59. And I get 12.1 degrees. I do have to stop and double check, make sure that's a unit circle value. Okay, I'm looking here, that's pointing mostly to the right. It's just a little bit more than 0, so that actually makes sense. So that's a unit circle value. Let's double check. I'm going to make a note that that's unit circle. What if I wanted a bearing? And I want to practice that now because in later questions, it's going to specifically ask for a bearing. So on a bearing, I would remember, and I'll change color so it shows up, this would be a bearing of 0, and this would be a bearing of 90 over to the right at east. So if this angle in here is 12.1, well, I am 12.1 less than 90. So all I'm going to do is do 90 minus 12.1, and I get 77.9. That's my bearing. Now, guys, you don't have to show any work to do that. I mean, I'd like to do it visually, but I didn't actually write out 90 minus 12.1. I typed it in my calculator to make sure it was 77.9, but that then produces a correct answer, so that's just fine. Let's do a few more examples. I hinted in the last video that we were going to use the dogs to learn some of this stuff and that we were going to be doing problems with the dogs. And so it is time. We are ready now to do a dog problem. And here we are. Haley, I should probably tell you who Haley is. Haley's this one over here. Haley pulls at a bearing of 354 with a force of 12 pounds because she's a little bit smaller dog. Moses, here's Moses over here. Moses pulls at a bearing of 84 with a force of 19 pounds. How hard do I have to pull on the leash? And in what direction do I have to pull so that the pups don't drag me to my death? And guys, I say death because this is the street right here. And clearly, if I let the dogs drive, Moses is going to drag me right out into the street, which he tends to. In fact, we walked around the University of Puget Sound this morning, and he did try to pull us into the street. So yeah, we got to be ready for that. So let's talk about how we approach a question like this one. If you haven't figured it out, it's a pretty strong chance that we're going to need to start with a diagram. So let's do that. So I'm going to start, I always draw out the 4 cardinal directions, north, south, east, and west, so that I can draw these in at a bearing of 354. So I'm going to remember that this is 0 degrees, and I'm going to make a note that we're doing bearings right now, so bearings. I'd encourage you to do that too, by the way, so you don't get confused about what these numbers are. It's really easy to get confused if you're not organized. So if that's 0 all the way to the right, around back here, that would tell me that 354 goes out in this direction, and I'm not drawing this to scale because I want to be able to write numbers. And if this is 354 and 0 is also 360, that tells me that's a 6-degree angle. Okay. Moses is pulling at a bearing of 84, which means if that's 0 and that's 90, he is 6 degrees off of 90. And so that's a bearing of 84. I'm also going to label in here what the magnitudes were. Haley's pulling with 12 pounds of force and Moses is pulling with 19. And then we need to figure out what direction I have to pull and how hard I have to pull to not die. So the easiest way to do this is let's figure out what direction, like what specific direction and how hard the dogs are pulling me. And then we'll recognize that I just have to pull in the opposite direction. So I'm going to do it like this. I'm going to try to figure out with Haley and Moses working together, how hard are they pulling? So I'm going to do H and I'm going to do M, and then down here I'm going to put D. D is for dogs. So Haley and Moses are the dogs and they're doing the pulling. So now we're going to try to figure out what those vectors are. So here we go. Let's try to write down Haley's vector. And what we'll do to start, we'll just write down what we know. What do we know about Haley? We know that Haley pulls with force of 12, and it's going to be 12 cosine something, and it's going to be 12 sine of something. What about Moses? What do we know about him? He pulls a little bit harder with 19 pounds of force. So he's going to be 19 cosine something and 19 sine something. We now need to go find the direction angles. Remember, the direction angles are unit circle angles. So I'm going to make a new diagram. I'm going to draw those same features. If that's 6 degrees, well, because on the unit circle, 0 is there, so that's actually 6 degrees. That's how we describe that direction. That was the one down here. That was 19. 19 was for Moses, so I'm going to go ahead and just drop a 6 in here for both of these now that I have the unit circle value. Remember, the reason we're doing the unit circle value is because we're about to type this in the calculator, and your calculator doesn't know what a bearing is, so that's pretty useless. I'm also going to draw in the vector for Haley over here. And if Haley is 6 degrees more than 90, well, she's at 96 degrees. So that's going to be 96 there and 96 there. So now it's time for us to add those together. Let's figure out how hard the dogs are pulling. So calculator time. I'm going to talk this out loud as I go through. We're going to treat it as 2 questions. So I'm going to start with 12 cosine 96 plus 19 cosine 6. And I get 17.6 when I do that. And then let's do the right side. So 12 sine 96 plus 19 sine 6, and we get 13.9 when we do that. When I get to this stage, I always like to pause and make sure these numbers are making sense. So I go back to the original picture. In this case, a picture was given with the question. This vector we just found suggests that the dogs are pulling to the right and forward. Visually, does that look like what's happening here? Are the dogs pulling me right and forward? Yeah, Moses is pulling to the right. Haley's pulling forward. I mean, yes, a little left, but not enough to cancel out the right. I look at my diagrams here. Are these pulling right and forward? Yeah, they are. I know this one has a little bit of left, but it's going to be more than canceled out by pulling to the right. So I'm in good shape. So what was the question we were asked? what direction do I have to pull, and how hard do I have to pull so that I don't get dragged to my death? Guys, it may not be obvious to you yet, that's the exact same question we just answered, where they said, what's the new speed and direction? And we did the Pythagorean theorem, or we did squareum, atom, rootum, we did tan inverse to find the direction. This is the exact same thing, and it's typical that these are the types of questions that will be asked. So all we're going to do, we're going to sketch out this resulting vector for the dogs. So it goes right 17.6, and it goes up 13.9. And we're going to find out the angle, and we're going to find out the magnitude. So magnitude is squareum, atom, rootum. I always like to do that one first because it's really quick and easy. So 17.6 squared plus 13.9 squared, squareum, atom, rootum. This is absolutely a calculator exercise, so I'm going to go ahead and type that in now. 17.6 squared plus 13.9 squared. Take a square root of that, and we get 22.4 pounds of force. Now, 22.4 pounds of force is describing what? It came from here. That's why I like to label these. That's how hard the dogs are pulling. So, is that how hard I have to pull? Yeah, it is actually. So, in this case, the amount that the dogs have to pull and the amount I have to pull, they're the same amount. So that is part of the answer to the question. That's how hard I have to pull. I think I can muster up that strength. I mean, I'm still here, right? So I must have been able to. We're also going to find the direction angle now, and we're going to use tangent to do it. So tan inverse of the y value over the x value, 13.9 over 17.6. Let's see what we get. So here I go. I'm typing it in. Tan inverse 13.9, 17.6, and we get 38.3. You need to be very careful. Is that a unit circle value, or is that a bearing? And is that a dog value, or is that a Mr. Boyden value? That came from right here, which means this describes the dogs in terms of the unit circle, and we know it's unit circle because it came out of the calculator. So that is not the answer to the question. Let's go down and draw this vector on a grid and see if we can find the actual bearing. If the dogs are pulling like this, and that angle we just found is 38.3, we should know that I have to pull in the opposite direction of that, 180 degrees away. So what we could do, we could recognize, and I'll put a little B up here to recognize this is a bearing chart now. I'm going to be doing bearings only on here, so 0 here, 90 there. So I could figure out what this is as a bearing. We could do 90 minus 38.3. And we get 51.7. So that's the bearing for the dogs, but I have to pull in the opposite direction. So that's 180 degrees away. So all I have to do is add 180 to that, and that will say how far I'm pulling. So I'm over here. I'm at a bearing, when I add that together, of 231.7 degrees. And so now we've answered the question. In order for me to stay alive, I have to pull in the direction of 231.7 with approximately 22.4 pounds of force, and that will neutralize the dogs, and they will be held in place. Let's do another one. Maybe you're ready to try drawing or attempting this question on your own. If you're feeling great, go for it. If you're feeling like you don't have this down yet, then feel free to wait and just walk through the example with me. Take notes, play the video at a slower speed if you need to, or hit pause, do whatever you need to, okay? So an airplane flies at 450 miles per hour at a bearing of 76. All right, let's make a bearing chart. I'm going to put a letter B here so I recognize this is a bearing chart. And on a bearing, 0 is there and 90 is there. So we are at 76, which means this is a 76 degree angle and a magnitude of 450. All right. The wind begins to blow 30 miles an hour in the direction of 172. Okay, 180 is down here, then 172, and no, it's not quite to scale, but 172, that tells me that that is an 8 degree angle. And we have a magnitude of 30. We are asked, with those two things going on, what's the new direction and speed of the plane? Cool. So that tells us we're going to add them together. We're going to add the plane plus the wind and get the result. And so I can start to fill out some things about these vectors right now. And that's what I like to do. I like to go get the easy wins. It kind of helps my psyche a little bit. So what I'm going to do is with the plane, we know that that is 450 cosine of something and 450 sine of something. We'll find the angle in a minute. Do not use that though. That's a bearing. And then the wind is 30 cosine something and 30 sine something. And so we need to go down now and find those angles. If we know those angles, the rest of the question is going to be exactly the same as the others that we've done. So I'm going to redraw this, and I'm going to make sure I understand this is a unit circle diagram now. And so I've got 76 degrees here, which means I can figure out what that is. They have to be complementary, adding up to 90. So 90 minus 76, that should be 14. So if that's 14, that means my unit circle number here is 14. I'm going to make a note. Maybe I should put a P here, so that was the plane and that was the wind. This is the value that goes with the plane. So we're going to go over and drop a 14 in here as our unit circle value. And then I'm going to draw in the wind vector as well. And if that's 8, I remember on the unit circle, that's 0, that's 180, that's 270, which means this is 278. So I can go drop 278 over here now. And so now that these vectors are totally filled in, it's calculator time. Let's do the addition. Let's find the resulting vector. So 450 cosine 14 plus 30 cosine 278. And we get 440.8. And then we'll do the sine or the y component. So 450 sine 14 plus 30 sine 278. And I get 79.2. And so now we're asked to give the new direction and speed of the plane. Again, speed's the easy one. Square them, add them, root them. So 440.8 squared plus 79.2 squared, square them, add them, root them. It's calculator time for that one. So 440.8 squared plus 79.2 squared. Don't forget to put the square root on there, please. And we get 447.8. And that's miles per hour. Let's double check, make sure that makes sense. The plane was going 450. It's dealing with a little bit of a crosswind, and it slowed down just a little bit. Yeah, that makes sense. That makes perfect sense. That's great. We also need to find the direction. While you don't have to draw the picture, I find that I'm really prone to getting them wrong if I don't. So I'm going to draw the picture. So we have a triangle that goes 440.8 to the right, and it's going up with 79.2. There's the vector. There's the angle. Let's go find it. So that would be tan inverse of the y over x. So tan inverse of 79.2 over 440.8. And so here we go. Calculator time. And I get 10.2. Now pause for a second. Why is it that if you circle that and give that as the answer, it won't be right? In this question, they gave us bearings, which means we need to answer the question in bearings. 10.2 is not a bearing. 10.2 is a unit circle number. Our calculator gave it to us. So I can quickly turn this into a bearing chart. And if we know that that's 10.2, and on a bearing that's 0 and that's 90, this is 10.2 less than 90. So 90 minus 10.2, and I get that my bearing is 79.8. So we were asked, what's the new direction and speed of the plane? The new speed is 447.8 miles per hour, and the new bearing is 79.8 degrees. Final example. Two degenerates want to rip a safe out of a wall. So they each tie a rope to the safe, and they start pulling on it. The first person stands 30 degrees left of center and pulls with a force of 150 pounds. The second person stands 45 degrees right of center and pulls with 210 pounds of force. The safe can only move straight out from the wall because of the casing that it's in. So what's the total amount of force being applied to the safe in the direction that is directly away from the wall? Wow, that's really tough wording, isn't it? So I'm going to show you how to draw this and how to understand the question. Okay, first things first. They're ripping the safe out of the wall. Do we know if they're ripping the safe right, left, up, or down? No, there's nothing here that says so. But it's not asking about right, left, up, or down. It's asking about the direction that's away from the wall. So what I'm going to do, and it's just one way of doing it, I'm going to say the wall goes like this, and there's the safe. And so the safe is going to end up moving away from the wall. So like there's a little safe in here, and it's being pulled on, and we want it to go out. So that means the direction away from the wall, that is the y direction, with the way I've drawn this. Now, could you draw it so it's the x direction? Heck yeah, you could. But I just haven't. Now, let's get the information in the question on the diagram. They each tie a rope to it and start pulling. The first person is standing 30 degrees left of center. Okay, so they're left of center. I need to put in something so we understand what center is. So dotted line here, they're standing 30 degrees left of center. And they're pulling with 150 pounds of force. What about the next person? The second person stands 40 degrees right of center. So they're out here somewhere. So now that's a 45-degree angle. And I guess they're a little stronger. They pull with 210 pounds of force. That's a 0, not a 6. The safe can only move straight out from the wall, and then, okay, the rest of it is just really simple. So guys, we have two vectors that are pulling. All we're going to do is we're going to add them together. We're going to figure out what that result is, and then we're going to interpret that in this context. One thing I do want to point out, a question that comes up in class sometimes, people say, wait, but isn't this like a subtraction because one's pulling right and one's pulling left, so we need to subtract the forces? We actually don't need to, and the reason is because when you choose the correct direction angle and type that in the calculator, it's actually already figuring out that it's left and right and up and down. So it's the calculator is taking care of all that accounting for you. So you can just always treat these as addition questions. So let's go ahead and get our two component vectors. Let's try to get our resultant vector. And so maybe I'll call this person 1 and person 2. We'll call this person 1, person 2. We'll find their vectors and then we'll find the results. And let's see what they're doing. So let's start filling in what we know. Person 1 is pulling with 150 pounds of force, so this is 150 cosine of the angle and 150 sine of the angle. But what's the angle? Now remember, it's unit circle. So if this person's over here 30 degrees, if that's 0 and that's 90, 30 more would put this at 120 degrees on the unit circle. So I'm going to drop a 120 in here. Let's go to person 2. Person 2 pulls with 210, so that's 210 cosine of something and 210 sine of something. Let's figure out their angle. If they're out here and that's 45, well, oops, not 40, 45. That's just 45 away from 0, so that actually is the direction angle. Except I've done that again, haven't I? So 45. There we go. And now that I'm all set here, I hope you're noticing the pattern. Now we're going to do the addition, although I should probably write a plus over here, so that's obvious. So now let's do the addition. I'm going to take a minute, type it in the calculator. So 150 cosine 120 plus 210 cosine 45. And I get 73.5 when I do that. And over here, 150 sine 120 plus 210 sine 45, and here I get 278.4. All right, let's go back and interpret this in the question. They say, what's the total amount of force being applied to the safe in the direction that is directly away from the wall? You know what? We kind of did ourselves a favor here in the beginning, realizing that was the y direction. Because what is the y direction? Well, this is x and that's y. So actually, the answer to this question is already there. So 278.4 pounds of force. That's the amount of force that's being used to pull it directly away from the wall. And y'all, that's it. This question is done. Okay, so that's 4 examples of applications that we can do. We saw speed, we saw force. Those are the 2 most common things we're going to see with vectors. Personally, I love these questions. I think they're super interesting just to see when you have a variety of things happening in one context, how you can simplify that all out to one direction and one magnitude. I hope you've enjoyed it too. I hope this video was helpful, and we'll see you next time.